angle of departure here. So simply we work on instance. Let me use black color. Okay. So we simply calculate is this, and from our equations, this is a single multiplicity. So phi of the departures will be equal to the summations of this one. What is this? This is the angle from the point, from the test point. We place our test point very nearby. In theory, I would say the nearby is that pretty much is close. So this kind of the short, very short distance compared to from here to here, then that is pretty much, we can, in this calculation, we can pretty much say this point is on here. You got my point? Okay, so in this way, we can, for this case, for this example, we don't have any zeros on the here, so basically this term will be 0 here. Okay, and minus the summation of this one. Then we work on this one. So this is our test point. So this is the test point and very close to here. Okay. So from here, this is the angle. Let me call this is phi1. And so that means here we can calculate and minus 180 degrees. Let me keep writing here. Minus, okay, so phi1 equal to 135 degrees. Because here this is J and this is this is minus 1 plus J. So here we can quickly determine that 135 degrees. Okay. Then the next one, what is phi2? Then we just scan through all the poles. So the next one, let me choose is this one. Okay.
45?
Yeah, this one is 45 degrees.
We just assume that E3 is 90.
Yeah, the third one is 90.
So do we always
From
assume
here.
that?
Because it's right on the top,
Yeah,
so
can
it's
we
90
always,
degrees.
Can we always assume that?
Always, because that is a complex
Yeah,
conjugate,
okay.
always on the top. So the third one. So the angle here, so there's a phi3 is 90 degrees.
Why is B2 45?
Oh, sorry, not 45. Pretty quick. Thank you. We can calculate. So phi2 here, how to calculate phi2? So phi2 basically determines this. Here is minus 1 plus J, and here is minus 3.
Yeah.
So from here, that should be, here you can determine the distance here is, the distance here is 2. The height here is 1, not 45. Okay, thank you. So here, this one should be, this should be arctangent, 1 over 2. Okay, the third one is 90 degrees. Thank you. Okay, so that is the whole thing here. Then we can do the calculations, and from here you can pretty much make sure the tangent arctangent of 0.05 will be the reading whatever from your calculators, because here we can see that is an acute angle. So we save here. So that one would be equal to so this angle is 26.6 degrees. Okay, so here this one will be equal to minus 135 plus 90 is 225, and 225 plus 26.6 is 251.6 minus 251.6 degrees. And this one, if we take the 300 degrees repeated things, this is 70. Is that right?
What about your minus 180? Are you going to do it at the end?
Did we subtract
And
180?
then, sorry,
Yeah.
so here is subtract 180.
30.
So that will be equal to how much?
So 31.6.
Minus 431.6 degrees. So this one, again, if we take the minus 346, this is, if we take the clockwise, this is minus
60.
minus 360, and then going further, so here this is the, basically is 71.6 degrees, right? Okay.
Should be up.
So from here, the departure angle is this one. So here we can draw is this. This is our starting point, and departure will be, the tangent is minus 61. So that pretty much like this, in this orientation, locally, going down. And that orientation is determined by this. Okay? So here the root loci will, this root branch will leave from this pole in this sense. So that is the increasing direction of increasing k. So from here we know it's leaving and approaching to here. So here we should have expecting kind of turn point. So the rule we can, from here we can schematically join it just like this. Okay? It will lead from there at the such specific angles. Yes.
Is there a way to tell which asymptote they go to without?
Yes, from here you can pretty much know the, because this is only 4th degree, it won't go kind of the distorting very much. So here, if we go from here, it will go to the nearby there first. Okay, and for this one, because of the symmetric, then you can quickly determine, then basically it has the symmetric, so that will go up. Okay, so go up and then turn around and then go approaching to here. And this angle locally is 75.6 degrees. Okay?
So the only difference between the departure and the arrival is?
0. So if this will be the 0, then the branch will go in. Okay, so here let me give the formula of arrival here. The formula of arrival is Q. Sorry, here I changed my symbols. Arrival is psi. We know we're using psi is to denote the angle to the 0. Okay, so let me change the symbol. The sign arrival will be equal to the summation of bi minus summation of psi I plus 180 degrees. Okay. And again, the two things is not so particular, it's not so special. And from our example, we simply start from the angle criteria. If we have any numeric examples, you don't have to stick with those kind of symbolic calculation. Just like you directly do the calculation with the numeric example, then we can see the same result. Okay. And the two formulas, again, is not so special. It simply is from there. Yes.
So multiplicity is the highest number of repeated roots you have?
Yes. So for this case, the T, the figure and the Q, the multiple.
Do they have to be complex conjugates?
Yes. Yeah. The angle of departure, angle of arrival, always about the branches coming to the complex conjugate 4 or 0. Because from here, we already taken care of the real axis, on the real axis, right? And so from here, we know this will be like this. And then remaining would be, how much time we have now?
4 minutes.
4 minutes? Okay. So the next one, we can determine, right now we have two branches going to the infinity like this one. And the other two branches should go to here, approaching to here and here. And that will be coming from the two branches. The two branches will meet somewhere and break it away. And break it away will go into here.
You gonna draw it?
Yes. So we determine how to find the breakaway point.
Yeah.
Okay, so somewhere, the breakaway point, so let me say the breakaway point is here. Okay, so here is the breakaway. Okay, so the breakaway point, they meet there, and then they're approaching, so pretty much like this. Okay, so in total, before we calculate the breakaway point, basically the 4 branches, pretty much like this. And the breakaway point is basically representing is the repeated root on the real axis. Okay, breakaway, break-in point, that representing, basically they represent which are the repeated roots on the real axis.
But you can only assume that's on the inside of those asymptotes, right? Because you're only assuming that, right? Because the thing is, it's only at S is equal, as S approaches infinity, you know it goes to that. But you don't know, do you know if it goes, like, more of an angle, kind of?
We assuming, and if we,
Yeah, that's just,
if needed, we can double check.
but it's an assumption.
Assumption.
Okay.
Not assumption, we schematically draw it. Okay, we don't care how the details, but,
Oh, you don't.
okay, so here the repeated roots on the break and breakaway point can be calculated by this. And the rule 5 continue to here. So basically that is we simply do the calculation is this one. dk es equal to 0. So S is the breakaway or break in point. And the breakaway break-in point, this equation must be satisfied. And we can do the calculation for this example here. So from here we can know the k is equal to, we get these things done, is minus s plus 3 and s squared plus 2s plus 2. Okay, so from the characteristic equations we have this. Okay, simply we take into this equation, we're asking this one equal to 0. Simply we take the derivative of, not k, k simply is a representation of a polynomial here. So we put into here as s plus 3, s squared plus 2s plus 2.
Can you, if it's an easy enough function, can you just, after you solve for
Yes.
the repeated, you can just assume?
You just do it.
Okay,
Yeah.
well, like, you don't have to show
Yeah,
this.
yeah. So from here, I can give you the s will be equal to repeated roots with repeated roots. S equal to minus 2.3. So next time we're coming back, then that'll be easy. We're going to determine where the intersection with the imaginary axis, and that one is a piece of cake. Great, we almost finished.